Hello, welcome to math class. In this section, 7.4, we are going to look at linear inequalities. Just in case you wonder where the section 7.4 linear inequalities falls in the chapter, there it is, right in the middle. And in case you were wondering what chapter 7 is about, chapter 7 is the basic concepts of algebra. Our objectives for section 7.4 are to graph an interval on a number line. You may remember number lines that look like this. Maybe a little bit prettier. So we're going to graph intervals on number lines. Next objective is to solve a linear inequality using the addition and multiplication properties of inequalities. This is going to be very similar to the way we solved equations. There's one small difference. If you multiply or divide by a negative number, that will make solving inequalities different than solving equations, but that's the second objective. And the third learning objective is to solve an application that leads to a linear inequality. In case you're looking at the first two objectives and say, when in the world am I ever going to use this? This last objective, you get a real world application. So when we have inequalities, inequalities are going to function very similar to the way an equals sign functioned, in that it's going to take an algebraic expression and it's going to relate one thing to another. Just like if I were to say 5 is equal to 3 plus 2, I'm relating this expression of 5 to this expression of. I'm relating their equality, or the fact that they're the same, or equalness. That's not really a word, but I'm relating it using the equal sign. So for inequalities, I'm going to use these four relationships: less than, greater than, less than or equal to, greater than or equal to. Now, before I go on, I'm going to give you my two complaints about inequalities. The first thing that always bothered me about inequalities was if I were to see just an inequality by itself, just walking down the street or whatever, I wouldn't know whether to look at that symbol and is that symbol greater than or less than. I would know that the small value goes on this side and the big value goes on that side. So I knew that because of the whole, hey, here's my duck, and now you're scared because I drew a duck. I knew which side to put the big value on and the small value on. What I didn't know was, what's the name of this thing? Is this greater than or less than? And then I had a teacher tell me this, and then it kind of helps me. Because in English we read from left to right, that's the way we name this particular symbol. So if I had this box and I was saying, whatever is in this box is greater than whatever is in that box, because I read this from left to right. Looks like I have a straight face or a frowny face or something. Because I read this from left to right, that's the way that we name this particular symbol. Very similarly, if I were going to name that symbol, I would say whatever is in this box is less than, and again, that's the name of that particular symbol right there, is less than whatever is in this box. So my first complaint was I could never tell what to call those symbols if they were by themselves, even though I knew the big value went on the big side and the small value went on the small side. So hopefully the way you read from left to right can hopefully help you remember that. My second complaint is that these things are called inequalities. There's the word, inequalities. That means they're not equal. And then when we come down to these, we say, oh yeah, they could be less than or equal to. So you go through this whole part establishing inequalities are things that are not equal, and then half of the section involves things that are equal. So I could say 5 is less than or equal to 5. That's not an inequality, that's equal to 5. 5 is equal to 5. How is that an inequality? I didn't name them, so you can't complain to me because it bothers me too. But just keep in mind, in teaching and learning inequalities, you can have things that are less than, or you could have things that are less than or equal to. It includes more. So unlike if I say x is equal to 5, if I say x is greater than 5, there's more than one answer to this. In fact, there's an infinite number of answers. So with an equality, I've got one specific value in this particular case that satisfies that condition. If I'm talking about an inequality, there is the potential that I have a whole lot more. So now that I'm done complaining about inequalities, let's go on to the next slide. So when we are solving an inequality, we're going to be looking for the values that make the statement true. And there may be more than one, as I made reference to. There may be an interval of values that make the statement true. Unlike the statement x is equal to 3, there's only one thing that I can put in for x that's going to make that true. That's going to be 3 is equal to 3. If instead I had x is greater than 3, well, what values can I put in for x to make that true? Well, x could be 4, x could be equal to 5, that would make it true. X could be equal to 6, x could be equal to 39 3/4, really ugly number, but it makes it true. So I've got an interval of values. I've got more than one value. In fact, I have an infinite number of different values that would make that particular statement true. So one way that we're going to show those is on a number line by graphing. So in this particular case, if we're showing the values on a number line that would make the statement x is greater than 3 true, it's any number on the number line greater than 3. One thing I want to point out is this book uses this parenthesis to mean it does not include the value. So if we were putting values in for x is greater than 3, we couldn't include the value of 3. And the reason for that, if I made the statement 3 is greater than 3, that's a false statement. That's not true. So I couldn't include the value 3. The way this book denotes that is with a parenthesis. What you may have seen before in graphing on a number line may have been an open circle. So you may see this on a number line instead. Again, this book uses the parenthesis. Different books use different notations. Just keep that in mind. Those two notations are interchangeable. And in a minute, when we get to brackets, if we were to have something like x is greater than or equal to 3, then it's going to involve a bracket here to say that you can include that. And then the other notation that is common would be to have a solid circle. We'll see that in a minute as well. The next two slides show different types of intervals. And I'm going to go through each one of these intervals and give a specific example. But before we go through our different types of intervals, let's look at a real-world scenario of an interval so that it's not just an abstract thing with scary symbols over here like set builder notation. I got this particular picture off of the internet, but it's a real world experience. I remember going to an amusement park and there was some sign that said you have to meet a minimum height requirement. Your height must be greater than or equal to 48 inches. You've got to be at least 48 inches tall, which means if h is equal to 47, you don't get to go on the ride. Well, what height do you need to be? Well, this interval or inequality is the answer. You've got to be taller than or equal to 48 inches. And I remember stretching and still being too short. It's a silly example, but this is an example of an interval. So in my silly case where h is greater than or equal to 48, that's an example of an interval. It's not one of these intervals on this page. It's the infinite interval on the next page. Another thing to note before we go on, set builder notation looks particularly scary. Number one, because they put it in curly Q brackets and they put this X out here and then they put a bracket. But the stuff that they put in here is probably the stuff that you're used to, and then they put the curly Q bracket in there. Set builder notation is saying we're looking at the set theory. We put it in curly Q brackets. We are looking at the set of values. Our variable is X such that, that's what the line means. It makes you sound important. Such that, and then it gives a particular condition here. And that's the part really we're going to focus on right there. Don't let all the fancy lettering scare you away. So here's an example of an open interval in set builder notation. 3 is less than X, and that is less than 5. Before I do interval notation, I like to see it on a graph, and I'm going to put my number line up here. When I do number lines, I always like to put 0 on my number line, just so I get my orientation or my bearing. There's 3, there's 4, there's 5. Didn't have to put the 4 in there. And if I put this in graphical notation, I'm going to do it my own way. They're going to do parentheses. Their way is probably better, but it's going to include the values between 3 and 5. And it's going to be an open circle because I can't include 3. 3 is not less than 3. So I can't put in x is equal to 3. That would make a false statement. So if I were to make a graph of this on a number line, this is what it's going to look like. You could also do this with the parentheses. I'm not going to do this every time, but this same graph could look like this. I like the other way better just because that's the way I learned it. But there's an advantage. The advantage to using parentheses is when you put this in interval notation, it is going to be open parenthesis 3, 5, close parenthesis. And if you notice, the parentheses map to the values that are there. So maybe you want to use open parentheses. For a closed interval, I'm going to do the same exact thing, except I'm going to say 3 is less than or equal to x is less than or equal to 5. And this is a closed interval because my interval is going to include both 3 and 5, both values on the end. So if I was making my graph for this, it would look exactly the same, except those would be shaded in. I'm failing at shading in, but there we go. Those values would be shaded in. That is what my graph would look like. If you were doing the brackets, it would look like this. And there's your brackets. In interval notation, I would have bracket 3, comma 5, bracket. If I were to do the same thing with half open or half closed interval, I would have this. 3 is less than or equal to x, which is less than 5. So if I were putting that on the number line, I worked really hard to just erase that one dot there, I would have an open circle there. My interval notation would be a bracket 3, because it includes the value of 3, comma 5, parenthesis. Doesn't include the 5. If I were doing the half closed interval, this would be 3 is less than x is less than or equal to 5. So my circle would be open here, and my circle over here would be filled in. And the way I would write this in interval notation would be open parenthesis 3, comma 5, bracket. Now before I do an example of a disjoint interval, let me give you another real-world example. Maybe a little bit silly, but disjoint interval sounds kind of complicated. So what does that mean in the real world? Let's say we have a ride at an amusement park and we only want small children and adults to ride on that ride. Maybe this is little bumper cars or something, right? So we put up our sign. So here's our sign. And on our sign, we say only people whose height is less than, and I'm going to have these heights so messed up, but just go with it. Notice the interval, the disjoint interval. Only people whose heights are less than 40 inches can get on this ride. Or your height has to be greater than 60 inches. And I've just discriminated against short adults or something, but just go with me here. What that would mean if I was looking at this on a graph would mean, here's my 0, people whose height is 40 inches, anybody who's less than that, apparently not equal to that, can go on this ride. And anybody whose height is greater than 60 inches, they can go on this ride. But nobody here in the middle who's between those two heights can go on this ride. So if I've got this and I want a disjoint interval, I'll say x is less than 40 or x is greater than 60. And that would be my disjoint interval. Here's what's going to look like on my number line, very similar to what it looked like before. If I'm putting this in interval notation, I'm going to have open parenthesis minus infinity, comma 40, all the values from minus infinity all the way up to but not including 40. Or, and that's what this fancy symbol right here means, or any value above 60. One philosophical math thing to note as we go to the infinite interval, and you saw it in the last one, when you're putting your brackets or your parentheses, if you're listing infinity, you're going to include it with a parenthesis. Or if you have minus infinity on that side, you're going to include it with a parenthesis. What you wouldn't do is you wouldn't have infinity and then you would have a bracket. And the philosophical reason for that is you approach infinity, you go towards infinity, you don't ever get there. I'm sorry for Buzz Lightyear and what he taught you, but you don't go beyond infinity, you just go towards infinity. And so you don't put a bracket because you don't want to say, oh yeah, when I get to infinity. It's not somewhere you get, it's like a direction you go. I'll stop philosophizing. If we have an infinite interval, then that interval is going to involve or approach infinity. And you can see that in the graphs here. As you go to the right here, you're going towards positive infinity, and you see that in those cases. As you go towards the left, if your arrow is pointing towards the left, you're going towards negative infinity. You also see that reference there in your interval notation, and that's going towards negative infinity. In this last case, you're going towards negative infinity, and you're going towards positive infinity, because you're dealing with all real numbers. So let's look at an example of each one of those. X is greater than 3. This is what it's going to look like on a number line. Here's my number line. So x is greater than 3. It's going to be all the values bigger than 3. If I'm putting that in interval notation, the smallest value that I have is 3. That a right there would be a 3. I would have a comma, and I would have an infinity and a closed parenthesis because this is going towards positive infinity, or an 8 that fell over sideways. If I was looking at x is greater than or equal to 3, my number line would look exactly the same, except that would be closed in. It would include the value of 3. I'm putting this in interval notation. It would be bracket 3 because it includes 3, comma, infinity, and a close parenthesis. Then if I have x is less than 5, let's get a new number line down here. X is less than 5, here is my number line. So I have an open circle. All of the values to the left of this would be in that interval. This is going towards negative infinity. Remember, positive infinity is that direction. So if I was putting this in interval notation, I would say I'm going everything from negative infinity up through, but not including the number 5. If I were doing x is less than or equal to 5, my number line would look exactly the same, except this would be colored in. It would be solid, or it would have a bracket if you're using that. And so my interval would be minus infinity, comma 5, and it would be a bracket. Let me revamp my number line here to do this last example. And I just added a 10 on there because I might use that in a second. But if I was representing x so that x was a real number, I'm representing all real numbers. So it's everything on the number line. So it's this number line that looks like a number line with another number line on top of it. Except it's probably straight, unlike my crooked line. How you might see this, where you have all real numbers in a disjoint interval, if you had something like this that said x is greater than 5 or x is less than 10. If I was writing that on the number line, x is greater than 5, it would look like this on the number line, everything to the right of 5. If I was writing this x is less than 10 on the number line, it would look like this, and it would be everything that is to the left of 10. If I was doing a disjoint interval, x is greater than 5 or x is less than 10. So I'm looking for values that would satisfy one of those or the other, or possibly both, but one or the other. It would look like what you see down here with this orange and this green, but taken together, it's going to be all real numbers. Any number that you think of for x is going to make this statement true or this statement true. So it would be all real numbers. Example, interval notation and graphing. Write each inequality in interval notation and graph the interval. And we're going to be overachievers here. I'm even going to put it in set notation. So I've got this value here, x is greater than 1. The way I like to do it is I like to make a number line first. I'm going to draw my own number line, all right? So here I have my number line, here's 0, here's -1, I have an open circle, and the arrow's going that direction. And that's what you see right there. They just use parenthesis. We will take that and put it into interval notation. So the lowest value I have is -1, and the highest value I have this little arrow, so it goes to the right forever, is going to be infinity. So there's my interval notation. And here is where I'm going to try to be an overachiever and draw curly Q brackets. If I want set notation, that's an ugly curly Q bracket, but live with it. X such that x is greater than -1, close curly Q bracket. So that would be my interval in set builder notation. Next problem. -2 is less than x, which is less than or equal to 4. I'm going to draw my own number line. My own number line might not be to scale. -2, it does not include -2, so it's an open circle. It does include 4, so it's a closed circle. It's going to be the values that are between there. And that is the same thing that you see here in this graph using a different notation. And building off of that notation to write it in interval notation, I have all the numbers greater than -2, doesn't include -2. And then I have a comma, and it includes everything up to and including 4. That's a bracket. So there you see your answer. And to overachieve here, x in set builder notation, x such that -2 is less than x, which is less than or equal 4, close curly Q bracket. Then I sound smart. That's set builder notation. A linear inequality in one variable can be written in this particular form, where a, b, and c are real numbers. Don't go around using numbers that are not real. And in this general form, you can replace that with any of the other potential inequalities. So it could be ax plus b is greater than or equal to c. If you are looking at the addition property of inequalities, the addition property of inequalities works the same exact as you have for an equation, and I'll show you for an equation. If you have a is equal to b, now that's not inequalities, but that's an equation, and I were to add some value c to both sides of the equation, I would have a plus c is equal to b plus c. If I added a c to the left-hand side, I have to add a c to the right-hand side. That's what the addition properties of inequalities is saying. If I have a particular inequality and I add c to both sides, and I'm going to get wild and crazy, and I'm going to say a is greater than or equal to b, just to show it doesn't matter really what the inequality is. If I add c to the left-hand side, I can add c to the right-hand side, and I'll have a plus c is greater than or equal to b plus c. That's the same thing that this is saying. It's got a different symbol there. So here is an example. Solve 3x plus 4 is greater than 2x minus 1. So the first thing I have to do is I have a plus 4 over here. I'm going to undo the plus 4 with a minus 4. If I subtract 4 from the left-hand side, I've got to subtract 4 from the right-hand side. The plus 4 and the minus 4 will cancel, so I'm left with a 3x on this side, and my minus 1 minus 4 becomes a minus 5. I'm going to subtract 2x from both sides so that I can get my x's all on one side. So on the left-hand side, I've got 3x minus 2x. That, of course, just leaves me with x is greater than, those cancel out, negative 5. So I have the inequality x is greater than negative 5. It didn't say to write this in interval notation. It just said solve. But that is x is greater than negative 5 in interval notation. Next, let's look at the multiplication property of inequalities. Multiplication properties of inequalities are the same as that of an equation with this exception down here. This exception down here is what makes solving inequalities different than solving equations. If I have some inequality, such as a is less than b, and I multiply the left-hand side times a real number c, and I multiply the right-hand side by a real number of c, what do I get? Well, it depends on whether the value of c is positive or negative. If it's positive, I proceed as regular, and I would have AC is less than BC. Everything is exactly the same. Here is where inequalities are negative. If I'm multiplying both sides by C, and C is negative, meaning it's the opposite, it changes direction. I won't show you my duck example, but the duck changes direction and starts swimming the other way, so the duck's going that way. Don't know really what happened there. Okay, duck's changing directions. My inequality is changing direction. So I would proceed the same. I would multiply both sides by C. So I would have AC on that side. I would have BC on this side. But whereas I had this particular inequality, A is less than B, because I multiplied by a negative number, I'm going to change the direction. So I'd have AC is greater than BC. So the multiplication property for inequalities is the same unless you're multiplying by a negative number. And here's a slide that is emphasizing this. So if I were to have this symbol, I'll just make it Q is greater than R. If I multiply Q times negative 3, just because I wanted to, not for any particular reason, then I would have to multiply R by negative 3, and I would have to change the direction of the inequality. If I had Z is less than or equal to M, just because I wanted to, and I multiplied Z times negative 10, because that would be fun to do, then I would have to multiply M times negative 10. I would also have to change the direction of the inequality. So if I multiply or divide by a negative number, the direction of the inequality is going to reverse or change directions. Let's look at an example. Solve the inequality 4x is less than 12 and graph the solution set. So to undo multiplying by 4x, I'm going to divide by 4x. So those cancel out, and I'm left with x is less than 12 divided by 4. I understand that that is 3. So I'm left with x is less than 3. And the way I proceed, I'll put it on a graph first. Put my 0, put my 3. X is on the smaller side of that. I put it that direction, and that would be my number line. And their number line has the parenthesis on it. If I'm putting this in interval notation, everything from negative infinity all the way up to 3 is going to be included in my interval. That's an ugly infinity, let me fix that. Is going to be included in my interval that would make that statement true. Let's test that. So if I choose a value, x is equal to, I'm going to pick a value so that x is less than 3. So if I pick x is equal to 2, it should make the statement true. So I'll put x is equal to 2. back into this equation. So I have 4 times 2 is less than 12. 8 is less than 12. Well, sure enough, it is. What if I put in x is equal to, I don't know, 12? Will that make the statement true? Well, that would be 4 times 12, put a little question mark. Is that less than 12? Hey Siri, what's 4 times 12?
The answer is 48.
Didn't learn my 12 table of area. Is 48 less than 12? And the answer to that is no, 48 is not less than 12. What happened? I put in x is equal to 12, but if x is equal to 12, 12 is not less than 3, so I have a problem there. So only values where x is less than 3 is going to make that inequality true. Let's look at an example of an inequality that's going to involve a negative. Over here I have a negative 2, so I'm going to divide by a negative 2. If I divide by a negative 2, I've got to change the directions of the inequality. And in this particular step, they did it all at once. So let me just do it in 2 steps. Take this and I divide this side by negative 2. So I divide that side by negative 2. I'm left with an x. On the right-hand side, I have 8 divided by negative 2. So that's going to be negative 4. And whereas before I had a less than or equal to, I'm going to change the direction. It's going to become x is greater than or equal to negative 4. So values on the number line that include negative 4, or anything that's bigger than that, will make this inequality true. Here are steps to solving an inequality. Step number 1, simplify each side separately. Very similar to what we did with equations. You're going to do distributive property. You're going to do what your dear Aunt Sally said and go in order of operation. You're going to combine like terms. So you're going to simplify each side. Second thing you're going to do is you're going to isolate the variable. You've got to get it by itself. So if I have something like 4x, the 4 is multiplied by the x, so the x is not isolated. So the way I'm going to isolate the variable is I'm going to use the addition property potentially for inequalities. There's another property that we did, which will be step 3. I can also use the multiplication property to isolate the variable. So if I'm adding, I want to use the addition property. If I'm multiplying or dividing, I'm going to use the multiplication property to isolate the variable. And what we have to remember with inequalities is we have to change the direction of the duck mouth, or we have to change the direction of the inequality if we multiply or divide by a negative number. Let's do an example. So the first thing I'm going to do is I'm going to simplify both sides. So we multiply this 3 through on both sides, and we multiply this 2 through. Remember, don't multiply the 2 over there. No, because the 2 is only going through the things inside the parentheses. And so on the left-hand side, when I multiply through, I get 6x plus 12 is less than 2x plus 6 minus 4. These are like terms. I can combine that together and get 2. So I've done everything in step 1. I've simplified each side. I'm now going to use the addition property. I've got a plus 12 over here. That's a really ugly 12, but I subtracted 12 from the left-hand side, which means I'm going to subtract 12 from the right-hand side, and I'm left with 4x is less than negative 10. I'm going to undo multiplying by 4 by dividing by 4. Now, because I'm dividing by 4, not a negative 4, even though this number over here is negative, I don't change the direction of the inequality because I'm not dividing or multiplying by a negative number. And I don't really like my answer here because it's an ugly number, but apparently it's the right answer. X is less than negative 5 over 2. And I will draw my own number line, 0. Here is negative 5 over 2, and it is going to look like that. And this is what it would look like. And lest you say, when in the world am I ever going to use this? Let's go into applications or some word problems. When you're looking at inequalities, these are going to be common phrases associated with inequalities. If you see this symbol right here, a phrase that will be associated with that is greater than. This symbol is less than. And this one may be a little bit more perplexing, but that is at least. And this symbol here is at most. Let's look at an example of that. Max has test grades of 77, 84, and 86. So here are Max's test grades. If he wants an average of at least 80, so that average that Max wants could include 80. After his 4th test, what are the possible scores he can make on his 4th test? And you see the steps that are there. And if we think about how is it that we find an average, the way we're going to find Max's average is it's going to be 77 plus 84 plus 86 plus whatever he makes on his last test grade. We're going to have to take all of those test grades and we're going to have to divide it by 4 because that's the way we find an average. And Max wants an average to be greater than or equal to 80. That's what Max wants his test average to be. So we've got our equation for our inequality. Let's go to the next slide. So look at that. They did the exact same thing there. So they've got that inequality equation. So we're going to combine like terms. And we're left with 274 plus x. When we add up all those values, we're going to multiply both sides by 4. And 4 times 80 is apparently 320. So I get a value of x is greater than or equal to 73. Max needs to score 73 or more on his test in order to get an average of 80 or more. And there we go. He must score 73 or more. And that's why we've got an inequality, because Max isn't just shooting for an 80. Max is shooting for an 80 or above. So if Max on his next test gets a 257, that would make this equation, of course, be greater than 80. So any value greater than 73 gets Max a test average greater than or equal to 80. And the last thing in this section is three-part inequalities. And I like three-part inequalities because three-part inequalities sort of visualize what you have happening. So if you've got a number such as 6, and you're saying -2 is less than 6, and 6 happens to be less than 8. You can see that visually with the 6 in between the -2 and the 8. So if you're solving a three-part inequality, like we will in the next example, you want to get it in this particular form. And you want the inequalities to be facing the same direction. So what you don't want to have something like this. You don't want to have like 6, -2, and you like this facing this way, and so that gets all goofy and confusing. All right, so you want your symbols pointing the same direction. So we want to solve this. -2 is less than 2x plus 5, and that is less than or equal to 9. To solve this three-part inequality, I have this plus 5 right here, and I'm going to undo the plus 5 with a minus 5. So I do a minus 5 right here. And if I do a minus 5 there, and here's where it gets wild and crazy, I've got to put a minus 5 over here, and I've got to put a minus 5 over here. It's like I'm got to keep it all balanced in 3 dimensions or something. No, not really that complicated, but I've got to do minus 5 on both sides of my three-part inequality. So I'm left with a minus 7, and I'm left with a 4 over here. Next thing I'm going to do is I'm going to divide by 2. And the reason I'm dividing by 2 is I want to get rid of that 2 that's multiplied by the x, which means I've got to divide over here by 2, and I've got to divide over here by 2. So I've got to make sure to do it everywhere. And so I'm left with minus 7 over 2 is less than x, and that is less than or equal to 2. I'm going to put that on a number line. I realize they already have a number line, but I'm going to do my number line like I like. Here's my 0. Here's my 2. My number 9 is not necessarily to scale. Somewhere over here as a negative number, I've got minus 7 over 2. I've got an open circle, and I know that x is going to be on this side of that. So I start going this way. Hey, x is over here. Do I go on forever? No, in fact, I'm going to come over here to 2, and I'm going to stop. It's going to include the 2. I kind of messed up with my line there, but there you go. And that is what my graph would look like. I was putting this in interval notation. You see it over here, but it's kind of confusing with the commas and they're close together. Or it's just really fun and I want to write it. I would have an open parenthesis, minus 7 over 2, and I would have a comma. Everything from minus 7 over 2 to the right, all the way up to and including the number 2. And that would be in interval notation. So in section 7.4, linear inequalities, we have graphed an interval on a number line. We have solved a linear inequality using addition and multiplication properties of inequality. And we have solved applications that lead to a linear inequality